Okay, welcome, my friends. I'm going to start with stuff we went over last Monday, I think it was. So this is the last part of section 2, which is benzene. It's a 6-membered ring. It has 6 carbons and 6 hydrogens, okay, which tells us it has 3 double bonds. It forms a conjugated pi bond, which just means it has 2 or more pi bonds that overlap and allow for delocalization of pi electrons, which you can see here. And based on just experimental data, we know that it's much more stable than alkenes. It has a stability that's more comparable to alkanes. And this is because of that delocalization. So it has a few resonance structures, if you'll remember. One is with the double bonds just 1 carbon apart, or 2 carbons apart. So you can have double bonds here, here, and here. And this also has this resonance structure if the double bonds just move between 2 other carbons. And you can have this resonance structure. But we know that there isn't actually 3 distinct double bonds on benzene. And instead, those pi electrons spread throughout the entire ring, and they all share equally, instead of just having distinct single and double bonds. So here's that structure again. We have 6 carbons in a ring, and each carbon has an unhybridized p orbital in the top and the bottom. And each p orbital has 1 electron each, and those electrons spread throughout the entire top and bottom of the ring, which forms a conjugated pi bond. And that's why it's so stable above alkenes, is because of that charge and that electron density is spread out instead of localized in a specific area. Because if you remember, charge makes things unstable. And the more space electrons have to move around, the less energy a compound has, therefore the more stable. Okay. So that plays into aromaticity, which just refers to the unusual stability in a compound, and that's determined by the number of pi electrons it has. So it follows Huckel's rule, which says if a compound's pi electrons, the number of pi electrons, fit the formula 4n plus 2, where n is a positive whole number, then the compound is aromatic, which means it displays unusual stability. So this first one you can see as just benzene, but for example's sake. So we can count the number of pi electrons. So you can do this by either counting the number of double bonds or counting the number of carbons, because each carbon will contribute 1 pi electron. So here we have 1, 2, 3 pi bonds. Each pi bond has 2 electrons, so that would be 6. Oh goodness, that's so much harder on my laptop. But okay, so it has 6 pi electrons, or you can just count the carbons. So I have 1, 2, 3, 4, 5, 6 carbons, also 6 pi electrons. Okay, so if I set up that formula, 4n plus 2 is equal to 6. Okay, then I have 4n equal to 4, n is equal to 1. So n is a whole number, meaning that that's aromatic, because it follows Huckel's rule. Okay, so this next one, again, you can either count pi electrons by counting the number of pi bonds or however many carbons. So right here I have 2 pi bonds, which have 2 pi electrons each. So I have 4 pi electrons. And I also have 4 carbons. So, which would mean each carbon has contributes 1 pi electron, so that'd be 4. So if I set up that formula, 4n plus 2 equal to 4, then I have 4n equal to 2, n is equal to 1/2, which is not a whole number. So that is not aromatic. Meaning it would be anti-aromatic, which means it's just a regular alkene. It behaves like an alkene, while aromatics behave more like alkanes. Does that make sense? Okay. So, next we talked about EAS reactions, which are electrophilic aromatic substitution, which just means it's a substitution reaction happening on an aromatic compound via an electrophile. Okay, so because aromatic compounds are electron rich, they can undergo reactions with electrophiles. So they're electron rich because of that conjugated pi bond. They have that whole electron cloud on the top and the bottom of the ring, where those pi electrons are delocalized, which means they're nucleophiles, which means electron donating. So they can react with electrophiles, which is electron accepting. So typically they're going to be either partially positively charged or fully positively charged. And these reactions work by just substitution, like I said. So one hydrogen on the ring can be replaced with a nitro group, halo group, or an alkyl group, which are the 3 reactions we talked about. So we can go over this mechanism. Let me get out my notes because I don't quite remember it, to be quite honest. Okay, so the product for this, and if you don't remember, this is just another way to write benzene. Instead of showing the individual double bonds, because that's not really the structure, just to write a circle in the middle, but that just means benzene. Okay, so our product for this is going to have 1 hydrogen on that ring replaced with a nitro group. Okay, and I'm also going to make water. So my mechanism for this, the first step is you need to produce your nitronium ion, which is how you're going to be able to put that on the ring. So we have nitric acid right here. It's a structure for nitric acid. And then we're using sulfuric acid as a catalyst, which is a strong acid, which means it dissociates in water. So I really have H+ ions. Okay, so I'm going to protonate that OH group right here. And I'm going to form, and this bond is going to break. I'm going to form nitronium and that hydrogen is going to combine with this OH group and form water, which is one of my products. Okay, so now we have our ring. Okay, and these pi electrons are going to come and take this nitronium. So the arrow is going to come from your ring to the nitronium ion. And that double bond is going to break. So I have nitro group added to this carbon. And this also has a hydrogen here. And then a positive charge is going to form on that second carbon. And this is a benzenium intermediate. Okay, so from here, my bonding electrons from this carbon-hydrogen bond are going to go to this positively charged carbon, and that's going to reform my double bond. And this hydrogen is going to come off as an ion. Okay, so my H plus is a catalyst, so that's why we reformed it. It was both produced and consumed in the reaction. And then I form just nitrobenzene. Okay. All right. We can move on. So the next one we talked about was halogenation. So my product for that is just benzene with a bromo group on it plus HBr, because this is a substitution reaction, so we have two products, and same with the last one. So my mechanism for this one, again, the first thing you want to do is make an ion to be able to put it on the ring, because you need an electrophile. So I have my bromine, my electrons on that. Okay. And we also need this compound to catalyze this reaction. So I have aluminum, bromide. Okay. So some of this pair of electrons is going to go to this aluminum here and form a bond between bromine and aluminum. So I have bromine to bromine to aluminum to 3 more bromines. So, and this is going to form an ionic bond. So this aluminum is now going to be negatively charged, as bromine is going to be positive. So from here, this bromine to bromine bond is going to break, and these bonding electrons are going to go to this aluminum. Okay, so I'm going to form Br plus AlBr4, because this bromine went to this aluminum along with those other 3 minus. So that's where our ionic compound comes from. So we have our electrophile because this is positively charged. Okay, so now we have a ring in our second step, or our next step at least. Okay. Okay, so again, the air is going to come from your pi electrons in your benzene, and it's going to go to the bromine, which is the electrophile. Okay, so your bromine is going to add, oh goodness, that is so ugly. Your bromine is going to add to one of those carbons. This also has a hydrogen here. And then again, a positive charge is going to form on that other one, which is another benzenium intermediate. Okay, so then this carbon-hydrogen bond is going to break, and those bonding electrons are going to go to that positively charged carbon again to reform that double bond. And I also have that aluminum bromide anion. So when this hydrogen comes off, it comes off as a cation, H+, and it's going to combine with one of these bromines. Okay, so I'm going to form my product. Sorry, I'm going off the page a bit. So this is my actual aromatic product. So this hydrogen these bonding electrons went to this carbon. So then this hydrogen comes off as just an ion. And it's going to connect with one of these bromines. Okay, so I form HBr. And that leaves me with AlBr3, which was my catalyst. Okay. All right. So the next one we went over was Friedel-Crafts alkylation. And he said you didn't need to know the mechanism for this reaction, so I'm not going to go over that. Believe me, you'll get plenty of practice with that. Second semester, there's like a whole section on this whole thing. But basically it works similarly to the other two reactions. It's a substitution reaction just like the other ones. So we have benzene, and how you put an alkyl group on a ring is you use a haloalkane. Okay, so we have an alkyl group connected to a halogen, and you again use that same catalyst from the halogenation reactions, and then your products, you're able to put that alkyl group on the ring, and then you form HCl. So I think he just wants you to know the products for that reaction for now until we go more in depth on it second semester, because it's a tiny bit more difficult than the other ones, but it's not too bad at all. Okay, so that was the end of section 2. And then Wednesday you started, or maybe not Wednesday, someday you started section 3, just functional groups. So functional group is just a side group on an organic compound that goes to a specific set of characteristics. So a few examples here is like a nitro group, halo groups, hydroxyl group like in alcohols. And these are formed by functionalization, which is a process to introduce a functional group to a compound. So all of those reactions we just did, halogenation, nitration, those are all functionalization reactions. Okay, so there's a lot of information on amines that you guys went through. So first, just like the general basics, it's derived from ammonia, which is NH3. And this nitrogen here has a lone pair of electrons on it. Can be classified as primary, secondary, tertiary, or quaternary, depending on how many carbons this nitrogen is connected to. So like down here, this nitrogen is connected to 1 carbon, 2 hydrogens, so this would be a primary amine. This is methylamine. If any of you have seen Breaking Bad, that better be familiar to you. You use it to make meth. Not that we're gonna make meth, but you know. Anyway, the next thing was hydrogen bonds. So hydrogen bonds are a form of intermolecular forces, which is just attractions between molecules. And it can happen between, if an oxygen, nitrogen, or fluorine is connected to a hydrogen, then it can form hydrogen bonds with something else. That's also oxygen, nitrogen, or fluorine. So amines can form hydrogen bonds with other amine molecules and also water. Nitrogen is more electronegative than both carbon and hydrogen, which makes their bonds polar. So it's pulling electron density towards the nitrogen, which is going to make it partially negatively charged. And amines can act as both hydrogen bond donors and acceptors. So here you can see a hydrogen bond between two to ammonia molecules, and these can happen with any type of amines. But this ammonia molecule is acting as the acceptor because it's accepting this hydrogen ion. So the compound that has a lone pair of electrons is the acceptor. It's partially negatively charged, and this hydrogen is partially positively charged, so there's an attraction here. And as you see here, it can act as both a donor and acceptor, because this one is a donor, and this one is an acceptor. Down here, you can see the hydrogen bond between ammonia and water. So your ammonia, this nitrogen is again partially negatively charged, which means it has an attraction to this water molecule where the hydrogen is partially positively charged. Okay, so you also talked about basicity of amines. So there are Bronsted bases and Lewis bases because of that lone pair of electrons on the nitrogen. So Bronsted base just means proton accepting. So it just means it can react with the hydrogen ion and form this, which is conjugate acid. And this can happen with any amines with whatever alkyl groups on it. A Lewis base just means that it can react with an electrophile, which also means it's just a nucleophile. A nucleophile and Lewis base is the same thing. It means it can donate electrons, so it can react with an electrophile to form just an amine plus an electrophile. Okay. So last thing you talked about before today was alcohols. So alcohols are formed by replacing one hydrogen on a hydrocarbon with a hydroxyl group, which is an OH group. And just like all the other functionalized compounds, you can classify them as primary, secondary, tertiary. But this depends on how many carbons the carbon connected to the OH group is attached to. So in this instance, this carbon is directly connected to the OH group and it's connected to one other carbon, so this will be primary. This is the carbon in this molecule that's connected to the OH group, and it's connected to two other carbons, and R groups just mean something with carbon. And on this one, this carbon is the one directly connected to the OH group, and it's connected to three other carbons, so it would be tertiary. Okay. Have any questions? All right. Well, as always, if you have questions, email me or text me or make a tutoring appointment with me. If you guys don't have anything, you can go.